so under the classes page, I don't know if Dr. Schwartz saw my email yet, but this lecture 14B, I'm going to go over slightly today. This is a lecture I used to go over a lot. This one is, this is not currently there, but hopefully Dr. Schwartz will update it today. All of these stuff regarding C Pro, all this stuff I would look into, especially this last one that says general comments regarding C. This is something that I just briefly wrote a couple semesters ago. And the reason I would mention you to read this, first, it provides some good resources for starting if you haven't already, learning C. And the last thing is there's 4 points that are requirements for whenever you're programming in C from here on out for the remainder of this course. The first of which I describe in one of my videos, supplemental videos that I posted. Compiler optimization must be turned off. Libraries, functions, anything. I'm trying to remember what this one says. To be honest, I don't know if we'll keep this second one. We'll have to talk about that, but we'll go over that today a little bit, just because I don't know if we'll talk too much about it. So it might not be fair to require that. We'll have to see. The use of standard functions like printf, sprintf, which if you're not familiar with, that's fine. But these are standard C functions, basically to simplify some things that you'll have to do for the lab. We're requiring that you do not use those. They're prohibited. And the last thing, all code must utilize predefined macros, which are basically the group configurations, bitmask, symbols, etc., that we've already been utilizing in assembly. We've never required it, but these are the complementary definitions within the C programming language context, which I also talked about in one of my first videos of the supplemental videos, but we'll see that today as well. And these also, we'll give these 2 files, but those will be available elsewhere too. So any other questions regarding that? I just wanted to mention that. And then, so look through all of these, look through the general comments, look through examples for a couple C examples if you're still struggling online. There's tons of resources out there, but we try to give you the most ones that are pertinent to us here in this class. And then software docs has at the bottom, or C right here, atmel x mega C. So if you get confused where I'm referring to there. Okay, that's all I want to share for that. So the first thing we're going to do is go through basically, since I don't have all the videos out yet, and since your first lab coming up is next week is utilizing C, we're going to try to do a couple most important kind of concepts regarding C in the context of this course first today. And again, that's not going to be probably everything you need to know. So please do look through these things, but we're trying to help you out and give you as much as possible now. And then after that, we'll talk a little bit about SPI and how the lab's actually going to be. So Wes, you want to go ahead and start sharing?
Okay. So basically, to start off, we want to at least give you some examples of using C for programming the XMega. So today we're going to do one example where we actually type code out and kind of talk about it as we go. And then later on in the lecture, depending on how much time we have, but we're planning on covering it, we're going to show you some details like about how Lab 6 will work, not necessarily how to make it work, but just things that'll be easier to, to show you how to set things up, which makes more sense when we get there. But
we already give you a lot of stuff to set up skeleton code wise for Lab 6. So there's a lot that if we show you here, it's like we're giving you the whole lab. We're not going to do that. But we'll talk at a high level, and then you should be able to work fine from the skeleton code. But Lab 6, by the way, is up now, and it does take some time. So please do actually start it after today if you haven't already, or after this lecture. And we're just going to be doing some kind of random examples here. The first of which I believe we're going to do is just showing how to set up a timer counter and toggle LED. And the main thing we want to show is basically both polling in C, polling for a flag, as well as setting up an interrupt service routine. And then after that, we'll do a couple other things. We'll show functions as we go and some various things. But again, this is not everything in C. I would really watch through the supplemental videos as they get posted, but also before then be looking up stuff. So just recognize that you guys have to start looking up stuff on your own too. Okay.
So This first program, like you said, it's just going to be something that's kind of random for the purposes of demonstrations. So in this case, we may have done something similar for assembly in one of the help sessions or something, but we're just going to toggle the RGB LEDs at a certain rate. So we'll show you how to initialize GPIO, in this case, the RGB LEDs, and then initialize a timer and create functions in C to run these initializations, which are, similar to subroutines in assembly. So we're gonna show you an RGB init function, a TCC0 init, and then after we do the example where we pull for the flag, we're gonna show you how to use an interrupt. So we'll initialize interrupts and then add an ISR.
So the first thing I guess we'll do is set up the relevant systems, right, Wes?
Yep. So we'll do RGB init to start. And this is
all he does is, I want to mention one more preface thing. So recognize, if anybody hasn't started really C yet, what we're about to write in are called functions, and these are basically an abstract representation of a subroutine using the C programming language. So these ultimately, when we use these functions, and we're going to quote unquote call these functions just like at subroutines in C, the compiler tool is going to generate throughout all of our C code representative assembly code of our application. So we're learning how to program this higher abstract representation. And then we need to kind of understand how the compiler works so that we know how to write appropriate code for our microcontroller. But when we call these functions, it's ultimately going to translate to a subroutine getting called, so on and so forth.
Yeah. So RGB init, this is, you guys know how to do this, but in C, we'll show you how you access the registers. So the registers are still called the same thing. Remember, in assembly, the way we access the registers was by using equates that were basically the register's address. In C, you can do it that way, but there's also a little more of a I guess complex way, but it's kind of easier to write.
Which I already mentioned before in my videos. Okay. But it ultimately comes down to, if you type out, can you type out underscore notation?
Yeah.
So the underscore notation,
the RGBs, we type port D outset.
If we want to turn them off, this would be the label in assembly, which still works here, representing the address associated with the configuration register port D outset. But in C, a more C-like way uses structs, and it ultimately comes down to using this dot instead of an underscore. And the main reason we do that, like I mentioned in the video, is we see this kind of autocomplete nature, which wasn't provided automatically by Atmel Studio in C. And this is going to be nice sometimes. We'll see this with the include file that we also will talk about. I also talked about in my video, but that will be a nice feature to have to be able to not have to open up the include file sometimes.
Yeah. And then, like we showed in our help session, we have a series we had include files for assembly that had certain equates that were convenient, like group masks or bit masks for the LEDs. So we went ahead and did something similar in this C program. So instead of equates, these are called macros. So we're just defining some string or whatever as some value. And these are more or less the same as the assembly versions or counterparts. It's just the syntax is a little bit different.
These are preprocessor directives too, but now this exists within C contexts. And we'll see later on too, if we don't see in this example, but macros can be symbols for any segment of code. So it could be a constant like we have here. These are all constants because it all comes down from the 4, 5, and 6, those bit positions. But you could actually have executable code. And macros, you'll see if you ever go later on in more C programming, maybe take micro P2, once in a while you want to make macros that are actually functions, which means that they're not subroutines and they'll actually get run directly in your code. So macros basically get copy and pasted by the preprocessor into your C code. So whenever we reference these names, the preprocessor tool is going to replace those names with their corresponding definition, which would be shown on the right here. So syntax is a little different, but we're just throwing out stuff to get you exposed. If you have any questions or concerns, you can ask us, but look it up in your free time too if we don't run into time. So I already went into this in the video a little bit, so I'm just going to kind of fly through the basic stuff. But we're basically setting this memory location equal to some value. So in C, we can basically just think that usually we're specifying the memory location we want to access or write to, and then we want to set it equal to, and then have this value that we specified as a macro stored into that memory location.
So the assembly equivalent would be like loading this value into a register like R16 and then using a store instruction to write that register's value to that memory address. It's just, a lot more concise and easier for a human to write.
Somebody asked a question, I'll just answer. So a macro is an external code being copied to our .c file when compiled. Not quite. It's actually internal. It's directly the code's there in that same file. It's just that it gets handled by the preprocessor tool. So right here, Wes, can you highlight the use of the macro? So here, yeah. That right there, the preprocessor is going to see that symbol and be like, oh, I know what that symbol is. It's defined to be that guy, which ultimately comes down to bits 4, 5, and 6 being set, which is hex 70. So that the preprocessor looks at that code and replaces the use of this label on the left with hex 70 ultimately, but that's the preprocessor that does that. So GM_GM stands for group mask. It's very similar to bit mask, except bit mask is used for a single bit normally, at least in the context of AVR. Group mask is for multiple masks of bits, which in this case we're using to basically do something to all the LEDs at once. We want to set them all to be off and then set them all to be outputs. And somebody else asked if we do port D_outset, wouldn't that be the address location? So yes, both of these actually end up being the same thing. You're accessing the address associated with some memory location, and the compiler knows to interpret that as basically a store to direct memory space instruction like STS or some other form.
I don't know if he was trying to get at like if this was just the address or if it's a pointer, but technically this is a pointer to that memory location.
Yeah. So I guess yes. So it is a little.
Yeah.
Okay. So yes, it is. I will say a tiny bit different from assembly, but ultimately it still gets translated by the compiler into some form of accessing an associated memory address. And really, it is just the nomenclature between dot and underscore, but it is more C-like if you do more programming to utilize this, and it is helpful. So we're going to recommend that you use the dot notation, but you could use the underscore notation. So, and I'm going to move on from here, but basically just trust our nomenclature right now. If you have any other questions regarding this, just ask us.
If you guys are curious, you can go in and actually see where these are in the include file. So, this is complicated, but at the end of the day, these are, this allows you to write to that memory location. If you want to dig through the include files, and if you're curious, you can, but we're going to kind of skim over that. So
this class is not about how to be pros at C. It's just we're exposing you guys to things so that you can maybe become pros pretty quickly after this.
Yeah. We're going to set the output values high because they're active low. We've done this a million times, and then we're going to do outdir dir set equals, and then we're just going to use the same thing.
We're setting them all to be outputs, or setting them all off and then to be outputs.
Yeah.
Just like before. That's all we care to do for init. So now let's just jump into, or we can go ahead and show them calling that.
Yeah.
So,
and then we define the function here below the main. And because of that, we need a prototype above the main program. And I don't know if we are going to cover that.
I haven't mentioned that before, but function prototypes are basically just declarations to the compiler, letting the compiler know, hey, if it sees that name RGB init, then it knows that there exists that definition somewhere. It's trusting that if it sees that name, that if you use that name later on, which we're going to use right now, that it's not going to throw an error and say, hey, I haven't seen that name used before. So in this case, it actually hasn't, the compiler, when it sees that, doesn't know the definition of RGB init, but it's basically just checking, hopefully, that the name is at least declared, and then it'll find down here the compiler tool, which we're not too worried about, will find the actual definition of that routine here. And if you're curious, just to throw out more stuff, the actual placement of subroutines in memory and stuff, it's usually handled by the linker tool. So that's another thing after the compiler just has certain semantics and syntax that it wants to check for to make sure your code adheres to C, adheres to the standard specified by the compiler, which in our case, I've mentioned before, is AVR GCC in my videos. But anyway, that's extra information. So what we want to do basically in our main program is initialize our systems by calling our routines. We do that with the following syntax. So in our case, scroll back down, Wes, to the definition. So to look at this function, can you highlight the first line? So this is a definition of a function, and it basically is saying the following. Let's define a function named RGB init that takes within the subroutine no parameters, which is similar to how most of the routines that we did in subroutines, once in a while we passed in registers and so on and so forth, but most of the time we took in no parameters. That's specified by this parenthetical statement and then the word void inside. And then also the function does not return anything. So most subroutines, like our initialization routines in assembly, did not return anything. And that's specified on the left before the name of a function and within the function definition. And the void keyword is used one more time. So now when we call this subroutine, we better not pass anything within the function. And that's used again with a parenthetical statement. So the void is basically going to tell the compiler, hey, if I were to pass anything into that, throw an error, because I've defined this function to not take any parameters. So this is actually how we would call the function though. And let's go ahead and start writing the function for TCC0 in it. So let's say again, for this arbitrary purposes, we're going to toggle all the LEDs every 250 milliseconds. So let's just set up the timer counter to do that. We know that count value we don't need to normally store, but we'll go ahead and set it up. One nice thing that I haven't mentioned yet in my videos is that with 16-bit registers in the context of an assembly, we had to do two different load and stores. We had to load to the low byte and then the high byte. In this case, in C, the compiler actually abstracts that away, and that's one little nice thing that we can have now in one concise representation. So we can access 16-bit registers in one line of code like this, and we're setting that whole 16-bit two memory locations to equal to be 0. And the next thing, let's say we want to do is actually set the period register. And just like in assembly, we can have the preprocessor do some calculation for us. So basically, to calculate 250 milliseconds, Wes can go ahead and start typing it out. We want to basically, again, do the system clock frequency, which we have 2 megahertz, which again, you could use macros for this, whatever. We're just not doing it in this instance. Divide that by some prescaler, which in our case, what did we choose, I guess?
We chose 1024.
Okay, and remember, this result ultimately for period needs to be fittable within 16 bits. And then we'll multiply that by duration in terms of seconds, which in this case, there's different ways we could represent it. But if we wanted to say 250 milliseconds, we could do 250 e to the e minus 3, which I don't think this was available in assembly context, but now it is in C. And the preprocessor, again, handles this code and says, okay, this is just a constant. I'm going to then write this to be a constant. Then it just directly translates that to loading that memory location with a constant. Okay. Beyond that, normal mode is set up by default, but we'll go ahead and do it and show you how a label for normal mode.
So and I'm not sure if the group configuration or bit mask is the same as in assembly, but in this case it's TC wavegen mode. Let's see, normal. Some of the group configurations from assembly are slightly different. Some of them are the same, so you just have to double check. But
and just as before, once we actually, I'll answer your question in a second. But once we actually you should make sure to go to dependencies. I mentioned this in my first couple videos as well. But if you go to dependencies on the right, and then find IOX, can you show them, Wes?
Yeah.
So IOX 128 A1U.H. This is the equivalent, basically in C context, for an include file for the relevant symbols. And here, again, you need to get used to control Fing through and trying to find the relevant group configurations or bit masks, etc., which the names you can kind of get from the manual. But this is, again, we're expecting you all, whenever there's some relevant value to find here within this file, we want you to utilize that. So when I mentioned earlier a requirement for using predefined bit mask, group configurations, etc., this is what we mean. So somebody asked, so don't we have to have the truncating issue like we did writing in assembly? We actually do, but in this case, actually, so a little different. So a good question. So the preprocessor here for C is actually a little bit more effective than the assembler preprocessor, at least in this manner. So here, this line of code should actually be handled well. Can you highlight the, yeah. Should be handled by the preprocessor pretty well. So it shouldn't actually truncate and go to 0 like before. Now, however, I do mention in one of my operators video that C does truncate when you do division if it utilizes, there is context in which truncation does occur, but here this should be fine. And I'll let you look at that up more on yourself in your own time or ask me offline. Okay, so besides this, Wes is just saying clear overflow interrupt flag.
So this is more pertinent for when we're actually using interrupts. It's not necessary to clear the overflow flag when you initialize it. I think we just showed this as an example last time we did this, just as a, fail safe. Maybe we'll get back to this when we do the interrupt version.
Okay,
Then,
you can just go ahead and, okay, I see. Okay, so here we just basically want to start a timer counter, and then we want to actually pull for the relevant flag. And then after that flag is set, we want to then, which you start the timer, you have that comment messed up.
Yep. What do you mean?
Okay, we haven't started the timer yet. Okay, I see. Yeah. Okay, so after we start the timer, we basically, just as before, simple, we want to pull for the relevant flag, and then we're going to actually toggle the LEDs after the flag's set. But here, let's start the counter by using Control A register, and we specified 1024 in our calculation for a prescaler, so we have to select that. This is an example of the group configuration for that. And so this is basically setting up. We set up all the systems as we want for this very basic example. Now, in this case, we want an infinite loop to happen where we want to continually wait for the flag to be set and then then toggle the relevant LEDs. How we do that here, I've specified also in a supplemental video. We use a while statement, and while one basically translates, no, we already have it. While one basically translates to an infinite loop. So this parenthetical statement can basically evaluate to always true. So while is checking for some true or false statement ultimately, and one gets evaluated to always be true. So the following code defined within the left and right brace will actually always be executed. Think of this just as at the end of the day, it executes some code, and then there's an R jump that jumps back up to a label somewhere in the relevant memory that starts the code over again. And that just happens over and over, just like in assembly. So, and here, the next thing we're actually going to use while statement for is we're going to wait for some flag to be set. So you can kind of get a vibe for what we want to do is we want to wait while some condition is true. And in this case, what do we want to wait for? Well, our flag, the overflow flag, we want to wait for it to be set. In other words, we want to wait for however long the flag is not set. So basically, we don't want to do anything until the flag is set. So to kind of prevent our code from going anywhere, we want to prevent it from, we want it to stay in this while loop. Before we do the while loop though, maybe it'll make more sense, Wes. Let's do something new. Can we toggle let's write the code for toggling the LEDs first. So let's say that once we actually wait for the flag to be set, we can just do just like we did in assembly almost, hopefully get the vibe for what we're doing here in C. We can write directly to the port D out toggle register and then specify the same macro that we wrote before, which this should again ultimately say 4, 5, and 6 get toggled. So what I'm why I had us write this just now, we basically want to write something above this line of code that's going to prevent us from executing that line of code, this line of code we just wrote, for however long until the overflow flag is set. So we want to create some kind of statement that's going to make the compiler, make the machine stay in this polling loop, basically, just as we did in the C assembly before we do this. So we do it as follows. Why don't we do the double equals first, Wes?
Okay.
So there's several ways of doing this. We're going to show a couple, and we'll then basically settle on a syntax and a semantics that we like normally and you'll see generally. So one way, we could basically load from the int flags register, which this would give us a whole set of flags for the relevant timer counter. And then remember, we only want to check the relevant bit, which is the 0th bit. So if you're not familiar already, we can bit mask with a specific bit mask. So when I use the term bit mask as a verb, what that ultimately means is that we're going to perform an AND operation with some bit mask. So Wes, can you go ahead and write out in a comment an example, because I feel like we haven't gone over that yet this semester. So for example, imagine that write out some value, Wes. Maybe do this on a new line because you do 2 different lines. And then we'll show them. So flying through stuff, guys, but if you have any questions, we'll just trying to save us time and go through as much as possible. So basically, imagine that, just for example, that the first value that Wes wrote on the first line, imagine that's the value we loaded that's currently within TCC0 int flags. Now here, I mentioned in one of my videos, basically C can you highlight the whole conditional statement or the parenthetical part? So C is basically going to check, it's going to evaluate the expression that's within this parenthetical statement. And it's going to check whether or not this is quote unquote false or true. Now in C, what is considered false is an expression that evaluates to 0, the numeric value 0. And anything that evaluates to a non-zero value is considered true. So here we can maybe see right away that the first value that Wes specified, if we imagine that the TCC0 int flags register had that first value, that is a non-zero value. So here, let's just keep in the back of our minds that by default, the while statement would get evaluated to be true if we just had TCC0 int flags, because that value, let's say in this example, is non-zero and would be evaluated as true. So we basically need to note that there are other flags in that register that could affect the evaluation of this while statement. So how we want to prevent those other flags that we do not care about, we only care about the overflow flag, to affect our conditional statement, what we do is we bit mask only the bits that we care about. And in this case, we only care about the 0th bit. And when I say the term bit mask, what that ultimately means is performing an AND operation with that bit mask value. And so what this ultimately translates to, this might be confusing, throwing a lot of stuff out. What basically will happen when we bit mask with that specific bit mask or group mask in general, all of the other bits that we AND with that we do not care about will be zeros. So ultimately, the result of that AND operation will force all of the bits that we do not care about to be zeros. Why is that beneficial? Because now we can guarantee that the value is only non-zero, in our case, when this bit is set. So either there's two possible values when we do this AND operation. That last bit could be a 1 or it could be a 0. And if it was a 0, then the resulting operation would be 0. And that's because, again, ANDing with a 1 will just keep and preserve whatever the previous value of that bit was. So in this case, bit masking is doing that generic operation of doing some AND with some bit mask or group mask in general. So the AND ampersand that Wes wrote is basically doing that AND operation. It's ANDing the value on the left with the value on the right, which again translates to 1. And this result will either be either 0 or 1, because again, the result only depends now on the least significant bit in this particular example. So in this case, it will be 0 when the flag is not set, and it will be 1 when the flag is set. Let me reiterate that. So can you highlight the last bit in the first line? The last bit.
Oh, the last bit.
Yeah. So that bit is the overflow flag in our case. Now, if that flag is cleared, when we do this ampersand operation, this logical AND, bitwise AND is what it is called in C, then the result would be 0. And in our case, that means that the flag is not set. Now, complementarily, it would be, if it was set, then it would be the overflow flag is set. Now, what that means in our context is we want, like we said before, we want to wait until the overflow flag is set. So another way of saying that, and I got a chat and I'll answer this in a second. The other way of saying that is that we want to wait for however long the flag is not set. So this is what we're going to do to show the first example of this. We're going to take the result of this that we just wrote, and we're going to check whether or not that result is equal to 0. So the following line of code, this what we just wrote here, is a valid means for waiting for what we're checking for. So I'm going to go through it one more time. So what we do is we read from the timer counter int flags register. Can you highlight that portion, Wes? We bit mask that with some bit mask, which ultimately will zero out all of the bits that we do not care about. Somebody asked a chat, which we are going to go over in just a second. Don't worry. And this result, the result of that bit mask, we're going to check to see if it's equal to 0. This ultimately is going to evaluate to be true whenever that bit is 0. So basically, we're going to wait for however long that bit is not set, which ultimately translates to waiting for the overflow flag to become set. Whenever it actually does become set, this overall statement that we just wrote, the parenthetical statement, will get translated. Can you highlight it again, Wes? This overall statement will get translated to a false value because it will not be equal to 0. And then we will break out of that while loop. So again, this loop is preventing us from doing any code until that statement is true. Now, somebody asked, can we do some other syntax? Yes, we can. This is actually not the syntax that we normally have you do. We actually have you do the following. We have you do the bit mask, and then we have an exclamation point out in the front. And basically what this is going to do is it's going to perform the bit mask operation, which, I'll highlight that again, Wes. It'll perform that. And again, in our case, that will either be a non-zero value or a 0 value. Now, the logical not operation, which is the ampersand or the exclamation point, which I also go over in my operators video, will basically, if it's a non-zero value, if the exclamation point is applied to a non-zero value, it will zero out that value. And if it's applied to a 0 value, it will create a non-zero value of 1. So basically, we can think that it will take any false statement, a 0 value, and turn it into a true statement, and any true statement and turn it into a false statement. So basically, if the bit mask operation is false, in other words, if the flag is not set, then we want to use the not operation to make that 0 a true value in terms of the condition. So we want to wait for however long that is not set. That's what we can ultimately translate this line of code to. Now, I know I'm saying a lot. This might be confusing, but we're not going to spend much more time on this now, and you can come back and ask this offline or review this video. But this is a very crucial but tricky to understand concept in C, we're getting used to in our microcontroller. So we wanted to at least have it recorded first here for this video. But we're going to move on, but just trust us that this will ultimately translate to waiting for the relevant flag to be set. But please do review this offline once we do this. And somebody asked, and I'll at least answer this chat. Yes, basically, as soon as that relevant bits that we're looking at becomes set in this case, we want it to terminate the while loop. We want to wait for how long that's not the case. And somebody said we would be able to use something like that. Would we be able to use something like that in an if statement? So in this case, remember that we basically want to wait for however long this is not the case. So if we just use an if statement, which we haven't yet talked about, but if we use an if statement, that'll basically only check it one time. And if it's not true, we could actually do that in this case. Can you show that, Wes?
Because it's a while one.
Yeah. So we could do one other thing, but we will tell you that this is not we're showing you how it generally, you'll see code written if you continue on with embedded systems or C programming. So try to trust most of our, we try to give you good instruction. So in our case, please do use the while statement. But in this case, the following could be done, but you would have to take away the not. So basically, if this result was 1, which would mean that the flag is set, then in that case, we can think, oh, well, if the flag is set, then we want to do our operation and then actually do that operation. But the reason we don't want to do this is because in general, there's a lot of conditional statements that we'll have to do, a lot of ifs, a lot of stuff related to this kind of stuff. So when you do if statements, you can see how the indentation gets bigger and bigger. You see how indented in one line when Wes did the if statement. You'll see when we do more and more conditionals that if you do nested conditionals or conditionals within conditionals, that your code gets farther and farther away. So this is one way of preventing that from happening if you do this while statement above it.
And in this case, since this is the only code that's in our main while one loop, it doesn't really matter. But imagine you have a full application, you have a lot going on in your while one. You're not going to get back to checking that flag until who knows how long. And the whole point of this is that you're waiting in that while loop to delay some amount of time. So if you're like writing to an LCD or some other device, you're not going to be actually delaying. You're just going to run all of your code, get back to it, check again. So it's not really going to function as a timer unless it's in this case. The
opposite can also be true too. And I'll just throw this out there. In this case, this kind of if statement can actually be very useful in some cases, in the same case that Wes brought up, where if you have a bunch of other stuff that you want to do within some big loop, which in general you want to try to avoid, you want to use interrupts instead. But in this case, if you had a bunch of other stuff that you could potentially do, and you didn't want to prevent your code from executing until one thing was true. So basically, if we didn't want to halt our processor at that while statement, but we wanted to maybe do other things as well, then in this case, an if statement would work well because we could say, hey, is the timer counter set? If it's not, maybe we want to do something else. But we then just don't do whatever was associated with the timer counter until that statement's true. So there's various ways. It depends on the application. Just throwing things out there. Not going to spend too much more time on this because we got other things to do. But somebody asked, you can use another while one that encompasses the if statement, but then that basically the original way. Yes. So somebody said you can basically, there's another way which we're not even going to show, but there's another way you could do while one and then use a break statement. But that's a very convoluted way of doing it. So trust us that usually the first statement that we showed, the while statement, go ahead and delete the rest, Wes, is a pretty effective way of doing that. It's a nice, clean, syntactical way in C. Okay, so in this case, again, we're going to wait at that statement until that flag's set. Then after it's set, we have to remember that when we're polling flags, we have to clear the flag. So the first thing we should probably do right away, remember when we're polling, clear the relevant flag. So we write to, in this case, int flags, and we write to the corresponding flag. It's important to note here that the equals symbol should be used and not the or equals, which we're not going to really spend too much time on if you're not familiar with that. But if you're curious, you can ask offline. But the equals symbol is important to use for our microcontroller here when we're setting a flag. And then after we clear the flag, now we can think, let's actually do the operation that we want to do. So here, the only operation that we're trying to do for this basic example is just toggle the relevant RGB LEDs. So we already wrote that. And then after that statement, we can look at that following brace statement symbol. And the brace, you can kind of think of it as the R jump back to the top of the brace or top of the loop. And in this case, the loop is the while one statement. And in our case, again, since we're using this kind of conditional check, but there's a constant true expression in the while statement above. Can you highlight it again, Wes? The one. This will always evaluate to that outermost loop being always true. So whatever's within the left and right brace here will always get true. Or equals, not equals. Oh, Dr. Schwartz is answering what I mentioned by why not to do the or equals. If you have any questions again offline, you can ask. Okay, so that's all we want to do for this example. Let's build this, see if it actually rewrote our code properly. If not, we'll figure out any errors. Okay, we got some errors. Let's walk through it.
Missed a brace potentially.
That's fine. Maybe a parenthetical statement. Let's see. So this happens all the time. Well, we just want to make sure. Okay, go down. What does it say? Expected. Go down more. More. That looks fine. Scroll up. Scroll up. It's probably is it a backslash you added? Here, oh no, I know what it is. Scroll up. You added that comment. That's a comment.
Yeah.
Got you last time too. Okay. Okay, build succeeded. So yes, thank you for mentioning that comment. I noticed that too. Okay, so in this case, this build, let's actually see that it works properly now. Wes can go ahead and just run the code.
Oh no.
Okay, so we've been having, since last night, Wes has been having some Atmel issues, or he has an older version of the board, and the programmer has been giving some issues. Let's see if it works. Cool, it works.
Okay.
Wes joined.
So we joined.
So Wes joined on his phone. If you guys see Wes's video, you might want to right-click and then you can double-click, I think, or you can click on the ... and hit pin video if you want to see a full screen version of his video.
Can we pin it? Does it pin it for everybody if we pin it? No. Okay.
No. So if you don't see it right now, go ahead and find his video. But we see that basically this kind of whitish, which doesn't look that way in our camera, maybe LED, whitish color is emitting from the LEDs. And this is basically, again, all the LEDs toggling at a rate of roughly, in this case, 250 milliseconds, which we might not be able to get the timing vibe from this just because of the delay in our camera feed.
We can change this value maybe. You want to try
it's fine. I think it's fine for this example.
Okay.
So somebody asked too, somebody told me too, we can spotlight this video.
Okay.
Oh, I did spotlight it. It says cancel the spotlight, I guess.
Okay.
I don't know if I did that or not, but maybe Dr.
Maybe also because I'm sharing it may not take over that.
Anyway, so somebody mentioned as well. Can you go back to the code, Wes?
Yeah.
That's
open for me, right?
oh, so yes, the while statement with a semicolon at the end, if you scroll up. This is basically, you can, whenever you don't want to perform anything within a while statement, you can, this what Wes just wrote between braces, if we didn't want to perform anything associated with the while statement, we just wanted to kind of use it as a polling loop, you can terminate it with a semicolon that basically translates and tells the compiler, hey, I don't want to perform anything, just do an empty while loop is what that's called. Mm-hmm. Thanks for letting somebody mention that. Okay, so beyond this, okay, this was a basic example. Let's now do an interrupt service routine associated with the timer counter. We're just flying through things, some random stuff that's going to be important for your next lab. So how we do this is, it's again easier in C, thankfully. But the first thing you should always do when you're going to use interrupts with AVR, with this particular microcontroller at least, is you go to the top of your code and you include the relevant include file. So by default, this first include file, let's just say, is it basically AVR/IOH includes that IOX128A1U.H file that we talked about before. And I also talked about this in one of my supplemental videos. And this file, though, unfortunately does not provide us with access to some symbols that we need to define interrupt service routines. There's another header file, another file by AVR called interrupt.h. And basically what this file is going to ultimately give us that we care about is a macro, which again, defined statement, called ISR, which basically the compiler and preprocessor is going to translate into some code that then will ultimately get translated into some assembly form that we have been doing in C, like setting the interrupt vector and setting an interrupt service routine label and so on and so forth. So ISR with a parenthetical statement is a macro where you pass in the parenthetical statement, ultimately a parameter that specifies the vector associated with the interrupt. So again, vectors, interrupt vectors, we have the same labels as before in assembly. So in our case, if we want to do an interrupt for the timer counter C0 overflow interrupt, we would specify that vector, again defined now in the IOX128A1U.H file. You can right click on this symbol and go to implementation.
Show that again.
It'll show you, it'll take you right to that file. And this, again, maybe it doesn't make sense how they're actually doing it. You can dig through the include file if you want more. But this ultimately will translate to what we want, what we've been using in assembly. In this case, the preprocessor is going to then take that and associate some subroutine or some interrupt service routine with this interrupt. It doesn't enable the interrupt yet, which we're going to have to do, but this will do the interrupt vector procedure and the whole setting up for when the interrupt is enabled, that it will jump to the following code defined within the left and right brace. So now let's imagine that we haven't set up interrupts yet. We haven't set up interrupts yet or enabled them, but let's imagine we have for a second. Maybe we can just go ahead and write the code. So if we did set up the interrupt, what do we want to do in the interrupt? Well, in this case, we just want to toggle the relevant RGB LEDs. So again, this interrupt service routine, we're going to basically set up to occur roughly every 250 milliseconds. And we basically, when that interrupt gets triggered, just want to toggle the LEDs just as before, which Wes wrote the same line of code already. And now the benefit of this, again, just as an assembly, we don't have to do any polling. So we can go back up to our main loop, and we can basically, for this example, do nothing. We can just basically have an empty while one statement that's always just going to be waiting and doing nothing. And then whenever the 250 milliseconds triggers or elapses, then it will jump to the relevant interrupt service routine, toggle the LEDs, jump back to the main loop, do nothing. So what we need to do now, though, is configure interrupts.
Somebody asked if an ISR needs a type, and the answer is no. An ISR is not like a normal function. It doesn't return a value or take any parameters. Just like you use it in assembly, you would never pass a register value into an ISR in assembly either. So,
yeah. And somebody said this makes the whole procedure so much smoother. Yes, this does ultimately. This is the great thing about C. Again, idea of programming in a higher level at more abstract manner. But there is a lot more details to learn about C that we'll cover today. So please do look up stuff on your own time. This is not going to be sufficient for everything. So what we want to do here, we're going to go ahead and let's say in the timer counter C0 init, let's set the relevant interrupt at the peripheral level. So we basically want to write to the int control A register, is it?
Yeah.
And we want, again, whenever we have a predefined register or a value, we want to use the group configuration within the relevant interrupt service routine, which Wes and I were just so used to these macros and stuff that we kind of remember them, but don't feel afraid to go into you will have to most likely at first get into the include file, get used to the naming, the nomenclature.
Yep. And you can generally start typing the name of the peripheral like TC_, TC0 underscore, SPI underscore, stuff like that. And you'll generally be able to search or find it. But like you said, just control Fing through the include file is usually the easiest way.
Yeah. And once you get used to it, get the hang of it, you'll kind of remember too. But the autocomplete nature is a nice thing so that you can kind of remember if you don't fully remember. So anyway, so that will set the peripheral level interrupt. But now we want to, let's say, have another service routine, or sorry, another routine, another function called interrupt init, INTR init, where we actually enable interrupts at the global level. So we just set low-level interrupts for the overflow interrupt. So let's configure at the global level, low-level interrupts. So we write to the PMIC control register, again, utilizing another predefined macro, which is low-level enable bit mask. And then let's now enable the relevant global interrupt enable bit, which in C with AVR, you have to use a macro to do that, but it's also predefined. And that's also defined within interrupt.h, I believe, which is SEI. So SEI, just as before, SEI instruction, but now we have to do these parenthetical statement to associate it with a macro, which again is defined within the interrupt.h file. So ultimately this, now if we call this subroutine or function in the main loop, which we want to do after we initialize all the other systems like usual, should now, if we run this, once we start the timer counter, it should still, we can put a breakpoint maybe, and, put a breakpoint in the interrupt service routine. Boom, it gets to there. So we right away, we know interrupts are working, and Wes can take away the breakpoint and show us one more time his code working.
Continue. Start video. Spotlight.
It didn't switch for me though.
Let me see. If I stop sharing, does it?
Yeah, it would.
Yeah. Okay. Cool. So we get the same exact result.
You can trust us if you don't, or you can implement it yourself if you don't
Yeah.
believe us. But more or less the same result. Maybe it's a little bit discrepancy, a couple microseconds difference in terms of interrupt service routine executing and stuff, but more or less the same functionality. Okay, so any questions regarding these basic things that we've covered thus far? We got about, I'm going to fly through other stuff really quickly. One other main important thing, really big important thing for the next lab, but again, there's going to be other syntactical things and other syntactical sugars that you're going to need to know for C on your own and look up. But again, hopefully I'll get all the videos out in the next couple of days for you all. So the next thing, if no questions, the only thing that will show you, if you, Wes, you have that other file with the RGB stuff, or do we not actually do that yet? Maybe show them the.
Yeah, if we're gonna do it, we're gonna write it out fully. Okay,
then let's just do show them that add function.
Okay.
So one thing you guys did a lot with pointers, which are gonna come up a lot in C. So if you didn't do the homework or you're not familiar with the pointers enough, ask questions office hours or offline. I'm gonna make a video soon on pointers, but if that doesn't come out soon enough, please do look up on your own. Pointers are a big deal for a lot of reasons. One reason's for passing in variables with functions, which I'm not going to get into right now, but we did just want to show really quickly, if you wanted to create a function, do you have that file, Wes?
It's not implemented, but the
add function, I was going to say.
The syntax is.
Just the add function was, or you haven't?
Like we have the structure for it, like the skeleton, but not the actual, so we can show like parameters and stuff.
We don't see it yet.
Let's see.
So basically all I just want to show and just kind of remind you guys, if you don't already know, with functions, we haven't showed any parameter passing yet or any return values yet, but we could use the following kind of syntax, which this is a random function, but in the parenthetical statement for the definition as well as the prototype, you would specify a various set of variable parameters that the function should take. And again, you would specify a type and then a variable name in the definition, where basically this would allow you, when you call this routine, to pass in values to the function. And there's various ways for doing this, such as with pointers and so on and so forth, which I'm not going to get into right now just due to lack of time. But basically the parenthetical statement in the definition, which Wes, can you highlight, specifies the parameters that the function is going to take. And then the uint8t on the left of the function name specifies that the function should return some value of type unsigned 8-bit integer. Which again,
we can probably just fill this in.
Yeah, do a return statement. With another thing to note, by default with C functions, You don't need to do return if it's void, if you're not returning anything. But if you are returning some value, you need to use a return statement and then specify the value that you were returning. So this is all
Again,
I wanted.
this is useless in C because you could just write this out as your type of code. You wouldn't need a function for this. We just want to show it as an
This
example with
function's useless,
parameters.
he means. We're just showing you parameter function.
Yeah.
Again, other things you need to know, but there's one other thing I want to cover before we maybe take a break and then do SPI stuff. And that requires me to share this PowerPoint that I mentioned earlier on the website 14B, lecture 14B. Let me go ahead and do so. Oops. So let me know when I share this, Wes, if you can see my full screen when I go full screen in PowerPoint.
Yes, we can.
You can see
And
that?
it's on the website.
Okay,
Yep.
This is on the website. Thank you, Dr. Schwartz. So there's a lot in this PowerPoint and Dr. Schwartz's PowerPoint that he has that you should look into if you haven't already, you're not familiar with C too much. But the very important thing in this thing, besides this first slide, which I'll just mention, this is a list of reserved keywords that you can't use for variable names, etc. And we saw like while and so on and so forth, if, other things, return, so on and so forth. You're not going to use all these in this course. But the one that we're about to talk about is the volatile keyword, which we see on the right-hand side. Volatile is very important for several reasons, and there's two contexts in which volatile is beneficial for us in this course. Now, basically, you can kind of read with me. Is there a way I can use a pointer or something?
The bottom left, like there's a little pencil icon. Or...
Laser color, laser pointer. Okay, so you see this?
Yeah.
Okay, really, there's only one reason to use volatile keyword: when we directly interface with hardware, which is what we're doing for this course. So basically, there's going to be some instances in which we write code that the compiler is going to be like, nah, you didn't mean to write that. I'm going to take it away. I'm going to optimize it away. Even if you have no optimization, you have optimization turned off. So in this case, we're going to use ultimately the volatile keyword to suggest to the compiler, which the compiler sometimes may not listen, but most of the time it will, that we're basically, the thing associated with volatile should not be, or it should basically tell the compiler, hey, this thing that I associated with volatile should be treated as such, which ultimately is going to translate to a following couple instances, which we'll go over. So let's just jump into examples to kind of make sense of what I'm talking about. There's going to be several different use cases for volatile, the most important of which in our context are the first two, which are memory mapped peripheral registers and global variables modified within an interrupt service routine, which this is probably nonsensical right now. We're going to show some examples. And then the last two are used, if you take microP2, the third is used most likely. And then the fourth, another example. Okay, so jump into example. First is the peripheral memory mapped register example. So basically, let's read the comments as we go. Let's imagine, and you guys are already familiar with pointers a little, let's create a pointer to, so if you're not familiar with the syntax, preg, let's define, p_reg, let's define to be a pointer, which is specified by this asterisk. Let's make preg a pointer to some unsigned 8-bit value in memory. And so basically this pointer is going to be used to specify the address of some memory location. And let's set that value equal to the memory location hex 4744, which this is not necessarily necessary, the syntax that I did above it, in front of it, but this is basically specifying that this constant value 4744 should get interpreted as an address to an unsigned 8-bit value. So this is a little bit more precise. So basically for this example, let's assume that at address 4744 in memory, there is some memory mapped peripheral register. So having done EBI and other stuff in this course, we understand that hopefully the idea of memory mapped registers, we've been accessing memory mapped registers such as the configuration registers for peripherals all this time. And let's assume for this context, there's some peripheral register at that address. Let's do the following for this particular example. Let's wait for the data within that memory location associated with, again, with some register to be equal to hex 37. So again, the important thing that we're going to come back to is that the value within this register, with it being a memory mapped register, we can think in general can change at any given time. Think about like flags for int flags. Values in those registers can change at any given time. So the following line of code will should wait until the value within that register is equal to 37. So basically this while statement reads from the memory location using this asterisk symbol It dereferences the pointer, gets the value of memory at that location, and it checks, is it not equal to hex 37? And if it's not equal to hex 37, ideally, we would stay in this while loop until it is equal to hex 37. And then when it is, we would break out of this while loop. Now, the problem that we're about to see is that the compiler has no notion of this being a memory mapped location. It has no notion that there's some register associated with that memory location that the value can change at any given time for that register. So basically, the compiler is going to be like, wait a second, there's no way that this memory location can change. So what it's ultimately going to do, we're going to see, is it's only going to read from this memory location one time. In this context, what we want it to do is continually read from that memory location. We want to continually check, hey, is that value in that memory location equal to hex 37? But in this case, we're going to see in a second, let's go ahead and actually go to the next line of code. If you wrote this in Atmel Studio in C code with no optimization, you would actually see likely something such as the following, which I actually took this from Atmel Studio. So the following line of code, let's LDS into R24, some register, the value hex 4744 from that memory location. So let's read from hex 4744, and then let's compare the value that we just loaded with hex 37. So again, if this is equal, we're going to have the 0 flag set, but then this is the following code that's going to be generated. Branch if not equal, PC -1. So PC, again, is a label associated with the program counter, where if we're at this instruction, PC is going to be the memory location associated with this machine code instruction. And the important thing to note, the problem is that we are going to ultimately jump back to this line of code, this one line of code, if the value is not equal. So why is that a problem? Well, in this context, what are we trying to do? What we're trying to do is continually load from the memory location hex 4744. So in this case, if they're not equal, our goal is to instead jump back to this first line of code, which PC -1 in this case is a problem. It's going to jump to this line of code, which will just basically compare against the same value forever and ever. So basically, if the value that we load from hex 4744 is equal to 37, it's always going to be equal to 37 in this context. We're never going to reload from memory, which is a big problem. This will not actually implement or compile to what kind of assembly code that we want. So how we actually fix this is as follows. We add the volatile keyword to the front of this pointer, and basically you can read it as follows now. You can say that P_reg is a pointer to a volatile unsigned 8-bit memory location. So basically, this is going to alert the compiler that, hey, preg is now going to point to a volatile memory location. So whenever you access the data within that memory location, that means the compiler should interpret, hey, that data could have changed. So instead now, we're actually going to get the following kind of assembly code, or something very similar. Instead, all that changes is now whenever the value that we compare against is not equal, we're instead going to branch two addresses up rather than one address up, which exactly does what we want. So as I say over here, if not equal, it will reload potentially new data from address 4744 before recomparing to hex 37. So in this case, it does exactly what we want, but the previous line of code without volatile was the problem. It did not give us that. So any questions on this so far? I can't see any chat, but is there a chat going on, Wes, or any questions? You can jump on the mic or ask. Anything so far?
Do you need all the casting in the right section?
Okay, the question was, do we need the casting? So
yeah, like that.
Well, to be more precise, you should have the casting, because some compilers it'll definitely give you a warning, or most will, but it'll probably work if you don't have the casting. But if you want to just know the more precise nature, to be more technically correct, you would specify that this value is associated with some address associated with a volatile memory location.
Is that the same as the ampersand?
It's the same as the ampersand. So kind of and not kind of at the same time. I'm not going to go into details right now, but the ampersand will point basically to some address, but you use that when you're using variables. So if this
Okay.
was a variable here, if you did an ampersand in front of the variable name, that would get you the address of that variable. But we are specifying here a constant for some address. So we don't need the ampersand because we don't want the address of this because this is the address.
Yeah, okay. Makes sense.
Any other questions before I continue? I'm not going to go into the second example too much just due to time, but you can look at this example afterwards. And I put a lot of comments so it makes sense to you all, hopefully. But again, this is important because we're going to use this in the last part of the lab for next lab. And this is something that in general with microcontrollers, embedded systems, when you write C code, you're going to have to think about this kind of stuff. But the next example, I'll have you all look at your own time. But basically the same is true when we have some variables that we want to use and interrupt service routines. So for this example, I'll just give a high level. Imagine you have some variable representing your course grade and then a Boolean statement that could either be true or false, defined to be 0 or 1, where you impress Dr. Schwartz based on your grade. So let's imagine you had some interrupt vector, Schwartz vect, that would, whenever it triggers, it would check whether or not your course grade is greater than or equal to 90. And if it is, then you suddenly impress Dr. Schwartz. The problem here is that the compiler, again, is going to have no notion of an interrupt service routine executing at any given time. So this variable course grade and impress Dr. Schwartz most likely will, when you read from that variable, it actually will not continually read from that every time you execute the ISR. So in this case, just like before, it would only load the variable into memory one time rather than multiple times. And that's a compiler specific thing, but most of the time that would be the case. So in this case, we would fix these issues by again using some volatile keyword with these two variables. So this is the two main examples for our course: peripheral memory mapped registers and interrupt service routines. And it's actually this example that, or this interrupt service routine idea that's going to be applied and used within the lab, in lab 6. So recognize this. Again, throwing out, exposing you stuff. Don't expect you guys to perfectly understand this yet, but we have to go over SPI a little bit. So any last minute questions before we go move to some SPI concepts? Again, this is available on the course website. Hope it made sense to some of you, or starting to make sense, and then you can look at it in your own free time. If not, I'm going to stop sharing. Okay. Stop sharing. Okay, cool. So we got so before we do the SPI, I guess what we'll do is we'll take a break, and then do you want to do the quiz? Dr. Schwartz, do you want to do the quiz now, or do you want to do it after the break?
Let's do it now.
Okay, so let's go ahead and do an attendance quiz now. But again, I would recommend you stay after the attendance quiz. So where is that, Dr. Schwartz?
It's the normal place. I'm just setting up the time right now.
So the attendance quiz is named July 16th, I'm guessing.
Yep.
And the question today is basically, it's not a magic number now. It's basically a magic faculty member.
It's just a faculty member.
Well, yes, but
not magic.
What is the magical faculty member of today?
No, does it say magical?
No, it doesn't. I'm just adding superfluous words. Okay, so I believe
Mysterious.
it'll ask you basically what is the faculty member of the day.
Just tell them the name.
Stit.
Stit.
And it's in all caps.
It's not available yet. Okay.
But is it in all caps? I'm going to type it in the
It
chat.
doesn't matter. It doesn't matter. It's a pull down. It's a multiple choice. Multiple choice. Go. It's available. Go. And then how long is the break?
Somebody said it's locked. Can we make sure that anybody have access to it?
Should be available.
It says locked until 11:31.
Oh, I did the wrong thing. Sorry. Try again. Try again now. Should work now. Does it work?
Yep. Looks like it's good. Let us know if there's any problems. And then after this, you guys, what do we say, 5-minute break or?
Yeah, we'll do a 5-minute break, and then we'll go over some high-level SPI stuff for the lab.
Okay, 11:37. How about 11:37? We'll come back.
Okay. So hop on after you finish the quiz for a little bit and come back.
Quiz is under, same place the attendance quiz has been all the time. Okay.
It was STIT. STITT. Two T's. STITT. I'll type it out. Yes, I'll preface my answer to somebody's chat message that Wes and I are very biased against Dr. Stitt because, well, first of all, he's going to be my PhD advisor starting in the fall, and we've worked with him for some time. But yes, he is really great. He's one of the greatest faculty members that we know of personally. I'm sure Dr. Schwartz would attest to that too. But yes, he teaches digital design and reconfigurable computing and other things related to FPGAs and reconfigurable computing, which if you're not familiar with, great source, great field of information to look at into. Great classes.
Yeah, he would win Teacher of the Year every semester if we allow him to. But he's allowed to win every 5 years. So every 5 years he wins. He is recognized as the best faculty member in our department for teaching purposes. And he does great research too.
He's okay at volleyball.
He's darn good at volleyball. He's our best volleyball player as well.
Can I ask a question?
What's up?
I know you guys said that we should be using like the bit mask names or like the group configurations if you can find it, like whenever you can. What if like we just happen to search and maybe there is one but we didn't find it? Like, is it like every single time it has to be used?
Yes, we want you to do your best. You'll be able to find it. If not, ask on Slack. But and there might be a couple instances in which there isn't one defined. But again, look at the manual, which we can show that since we're having a break right now. But again, look to like the registers within some manual section, and again, they'll tell you what the group configuration name is. That's what should be.
That'll match for C.
Yeah, it should. I mean, their goal is that they defined the names in the include file based on what they put in the manual. So in this case, for instance, this register control A for timer counter C0 or timer counter 0 system tells you, hey, the bits field clock select, which is part of also the name in the group configuration, and the group configuration actually tells you the name. So Wes, can you go ahead and look up like either clock select or div1? I'll stop sharing.
Yeah, I mean, that's how I've been doing it so far. I just wanted to make sure.
I'll show it again just if anybody's watching right now too, but that's how you do it in general. I would start with the group configuration name because that should definitely be the same. Some of the bitmask or some of the.
Are you doing a specific example or?
Just look up in the include file. I mean.
Okay.
Now you have to be careful for anybody here that's listening, just like in assembly, that there are some very similar defines for other systems as well, like the RTC system. So in instance, if you did div 1, Wes, there's RTC prescaler, which might end up, it is the same result actually, if you look at the manual, but in this case, that is a bad macro to use, because again, the point of macros also is to kind of provide readable code to the application developer or developers, or for yourself in the future. When you look back at the code, or a TA, if they're helping you see right away, hey, that will translate into the value that I care about. So yes, we're forcing you for C. Assembly, we didn't care. Now on exams, we won't force you to use these, but it would be helpful. Now on exams too, if you do choose to use these, we don't in general with programming questions and lab quizzes that we'll do, we don't grade entirely on syntax. Now, if it's entirely incorrect syntax for C or assembly, then we'll take points off. But if you had like one letter wrong or something for some group configuration, we wouldn't take points off.
But let me say, if you don't use group configurations, you're going to make your Pi work harder. And when you make them work harder, sometimes you don't get quite as good of a score. So using group configuration is a very nice thing to do, and you get better partial credit. So I would strongly encourage it. Again, if you spell it a little bit wrong, it's okay.
Yeah.
And I will mention, kind of complementary to that, because we mentioned on the front of the exam or front of lab quizzes too, if you write nonsense, we're going to take major points off. So keep in mind, a Pi might look at might be like, oh, this is fine. And you write some BS for some free response question, but then later on you say something really wrong. And the Pi's going to think, wonder if they actually knew what they're talking about in the previous one. Go back and reread it. And if it's questionable, then say, always act responsibly and try to help your Pi out too, though. Separate point, but similar. I'm going to myself use the bathroom, and I'll be back in 2 minutes.
Oh,
Mute yourself, Dr. Schwartz.
We can mute him too, I think, if it ever comes to it. He starts talking too much,
Get out of here.
got some,
Oh,
it was a call about trying to sell me something. I hang up after 3 words. So.
What'd you like? Beep.
We've been trying to reach you. We want to sell you insurance that ran out on your car. Okay, I think we're at 11:37. So
I'm just answering one question now. Okay, so we are back, guys. Okay, we are going to now cover at a high level some SPI stuff, which again, we're not going to give too much details.
And at a high speed.
High speed too. Okay, so first, boom, go ahead and share your screen, Wes, OneNote.
Okay.
We're going to show at a high level, what are we doing? SPI communication protocol, synchronous serial communication protocol. We're going to communicate using the SPI protocol with an external peripheral. In this lab, we are going to use an IMU device, inertial measurement unit, that's going to contain an accelerometer, gyroscope. And the chip name, the specific IMU, is LSM6DS3. And basically, the important thing to note is that this chip can be configured. It has internal registers just like our other, our X Mega or microcontroller has itself. It's also memory mapped registers. So basically, whenever we want to configure this guy and get data from that guy, that's the guy that's going to do acceleration data and gyroscopic data, et cetera. We're going to want to access or communicate with this device. And how we do that is using the SPI protocol. Why? Because the chip was designed that way. So basically, we need to communicate with the chip using SPI. It also accepts I2C, another synchronous serial communication protocol, but we're just going to use SPI. So in this diagram, we're showing the relevant 4 signals, and there's a 5th that we'll talk about in a second, that are used for SPI. So chip select, slave clock, MISO, MOSI. So MOSI, again, is data going to the slave or the peripheral, and MISO is data coming from the peripheral. And the int1 signal that Wes drew, we're going to ultimately also use that for the last part of the lab too, which is going to be able to be set or configured an interrupt signal, just like we've been utilizing for peripherals within our microcontroller. We're going to configure some interrupt signal within the LSM via some memory mapped register within the LSM. And that will cause, whenever there's new accelerometer data to be read from the device, it'll send that interrupt signal, which that interrupt signal on our micropad is configured to connect to a specific I/O port pin. And just like we did before in a different lab, we are going to have a interrupt, I/O port interrupt set up to trigger on that specific pin that's connected to that relevant int signal from the LSM. And how do you find that? That is going to be on the out-of-the-box robotics backpack schematic where this IMU is located. So to reiterate, the IMU is located on the out-of-the-box robotics backpack, and the schematic is going to tell us certain details about this device, the LSM, which you're going to have to look up very much for the lab, as well as the data sheet for this device. So the first thing we want to note is, Wes, do you have it up, the 8331 manual SPI?
Yep.
So we're flying through stuff, and if you have questions, holler at us, preferably Mike, so we know for sure, but go ahead, ask him.
Let's see, 8331.
So what we want to do first is remind you, we already covered this in the videos, relevant videos, but SPI system, the SPI system is just in the microcontroller, is used to emulate the SPI protocol in various ways. And just like Wes said before too,
Chris, we lost you.
Okay, can you hear me?
The order of the data bits, all this stuff you have to configure on your own. Okay, so looks like Chris is back. I've showed them the time diagrams here and the fact that they have to compare them, and I made it obvious that we're not showing them exactly what to configure. We're just telling them where to look.
Yep, and we're trying to give you a high level point, but you will have to read these documentation.
Yeah, we've got 17 minutes, so.
No, remember we got 12:15.
Oh, 12:15. Okay, cool.
Yeah, we good. Okay, so cool. So the main thing we want to mention, or the main thing I was trying to get to, is that maybe Wes already mentioned it. Again, there's going to be configuration registers within the LSM that we want to configure and access, like for telling it to turn on the accelerometer, for telling it to give us data from the accelerometer, so on and so forth. And the SPI signals are going to be used to specify that. But first, go back to that, actually, Wes. So section 9 in this data sheet, go back, actually lists the relevant configuration registers, which we're going to have you look through, but there's just only a few that you're going to have to utilize. And these, again, have addresses just like we've been utilizing memory mapped registers for the X Mega. So basically, whenever we want to write to some particular register, which go ahead and show the HUMI register. So we're going to pick out one particular register, which you're going to utilize for the lab to check whether or not your SPI communication is working with the device. That's called the WhoAmI register. And basically, this register will always read back the same value representing the device ID, which turns out to be hex 69. So hex 69, WhoAmI register, we're going to read from to verify our device, to verify our communication is functional. So basically, recognize hey, if we want to read from that register, we're going to have to tell the LSM that we want to access that register. How do we do that? Well, we have to look at the SPI timing diagram, which is section 6.2, figure 8. And basically what this is telling us is the protocol that the slave expects. So basically, can you zoom in a little bit more? So the important signal let's look at, well, let's start from the top. Chip select, again, we know enables the device. It's actually looking for that falling edge and rising edge, the slave is, to know when to actually start receiving and getting data. Now the SPC, another name for slave or serial clock. Serial clock is going to actually tell us to transmit data from the master to slave, or the slave to master correspondingly. SDI, slave data in. So here's where it gets good. We can note, and it explains this below, that the first byte of data represents two things. The first thing, the first bit, represents whether or not we are going to read from the device or write to the device. If we read from the device, we want that bit to be set. So you want to actually start ahead and drawing over this, Wes?
Yeah, let's see.
We're just giving one particular example for the example we're going to do today in class. We're just going to show you how we're actually using SPI to read from it. We're not going to be writing the SPI code. We're just going to see the function.
I closed Zoom on my iPad, so I'm going to need a minute to join back.
No worries. So I'll explain while we go, as we go. So the first bit, think we want to be a 1 in our example. What we're going to do for this example is read from the who am I register to show that we actually get back the data from the slave. So in this case, read bit would be set. And then the following 7 bits specify the internal address within the device that we want to access. So in this case, we look at the register description section of this data sheet. We saw that who am I in our case is hex F. So here we would specify 0, 0, 0, 0, F, or sorry, 3 zeros, 0, 0, 0, and then all ones after that. So there
annotations disabled for this, so I can just draw on the PowerPoint, I think.
Okay.
My mouse. Signature, no. Highlighter.
Oh no, you're gonna have to do like a comment maybe, but
Go to edit or comment. Yeah, comment is a good place to do it, but you can go to edit and then
edit
on the
text.
right side.
on the right side.
Oh, edit on the right side.
It's
The bar's in the way. Okay. Edit PDF. No, I don't have Adobe Pro. Do I need Adobe Pro? Yeah, it's going to ask me to get Adobe Pro.
Forget this.
Okay.
Okay, so
Whatever.
okay, so we're gonna have the read bit set basically. That's we got to recognize that when we're accessing some register and reading or writing, we have to specify this data to the LSM. And the protocol specifies, hey, the first bit's gonna be specifying, are you reading from or writing to the device? Then there's an address that we're accessing. If we specify we're reading with the read bit, then the device is gonna know, hey, we're going to read from that address. So in this case, the first byte of data is going to be hex 1F for 8F, hex 8F, because the most significant bit of this first byte of data is set, and then the last least significant 4 bits are set as well. So hex 8F. And then after that, the slave by this point, when it gets that information, knows that, okay, now on the next clock signal, I'm going to start clocking in data associated with that register. But in this case, remember, Wes mentioned this in the video, his video, whenever we're reading from some slave, we still need to transmit data, but the data that we transmit does not matter. When we're trying to read data from a slave, we actually still have to write data to get back data, but that data is arbitrary. We're going to write, in this case, I don't know if we do hex 37 or hex FF, but we're not actually going to show that. But you can write any form of data. So the data that we write here is going to be garbage, but the important thing to note now is that the last signal, SDO, at the same time, remember, at the exact same time that we transmit some bit to the slave, we're going to get some bit from the slave. And the data that we see in the last signal, D07 or D07 through D00, is the byte of data associated or stored within that relevant internal register of the LSM. So we're basically going to shift out data from the LSM using this protocol, or we're going to write data to the LSM using the write bit with that bit cleared. And in that case, the data that we get back from the slave will probably be garbage. So in that case, just recognize there's the two complementary, the same protocols used to read and write. It just depends on what you're writing, and you have to think about what you're reading and writing. You probably other points to mention, Wes, but anything else right now?
Yep.
Okay, so we wanted to at least show this to get you in the mindset. You're going to have to look at the 8331 to figure out how to configure SPI to communicate with this particular device and its protocol. And then you need to recognize, hey, whenever I want to configure some register, I need to create a function that's basically going to set the read bit when it transmits data. So basically, remember, SPI is going to transmit 8 bits at a time, 1 byte at a time. So the first byte of data is going to represent the read or write bit and the address that you're accessing within the LSM. And the second byte of data is going to be the data that you're either writing to the device or garbage data to basically just read from the device. So ultimately, this is important to reference, but there's going to be other sections to reference as well. But does anybody have any questions before we actually show you just at a high level? We're going to actually measure these signals too using our DAD, which you're also going to do in the lab. But we want to at least give you context for what we're doing. Any questions? Jump on mic or chat.
Okay.
Okay, so what we're going to do is basically just show you high-level code that is not going to really make you understand what the code means. We're just showing you we are using SPI. So basically, as follows, we are calling some arbitrary function that initializes our system, which we're not telling you how to do that, which you don't have to make this function. We just wanted to abstract away the details from you, keep it short and simple for this point, this lecture. And then what we're going to do is create a variable for the purposes of testing, reading from the who am I register. So we're going to create a unsigned 8-bit variable named test. And then we're basically just going to set test equal to the value that we read from the LSM 60S3. And this function you're going to write for the lab basically is going to specify a register address. And then it's going to use that address and write, or it's going to write that address in the read bit. And then it's going to actually read the data from the LSM. If that's successful, you will actually get the data. Show the data that we're getting. You will actually receive. No.
Register. Oh, what?
Yeah. Just go to no. Go back to the yeah. You will actually receive whatever is within that register, which is called DO7 through 0 here. Now, like Wes was showing, if we go back to register mapping, that DO7 through 0 is going to translate to hex 69 in our case. So we are expecting hex 69 when we read from this configuration register, who am I? And we're going to show that, as well as on top of that, after we do this, we're going to use the DAD to actually see the protocol being utilized by our microcontroller. So,
and we can just mention this real quick, but the registers are defined in this file that's provided to you in the zip folder that's on the website. So all of the addresses of every register is included, so you can just reference these names instead of having to memorize the addresses. Just like
the AVR include file we've been using.
Right.
So let's put a breakpoint on the while loop after we actually read from the LSM. Do you have optimization?
I haven't changed it since yesterday. But
so remember, every project you create, you're going to have to go to optimization, like Wes just showed. And I covered that in one of my first supplemental videos, if you're not familiar already. Okay, so he basically broke and at that statement, and we can see using a watch window, test is actually equal to the value hex 69. So not super exciting, but this is going to ultimately, when you do the lab, this is going to be used to test whether or not your read functionality works, which is going to be an exciting feeling when you see that for the first time, when you actually write your code. So keep that in mind. Now what we're going to actually do is show you also how we're going to somewhat measure signals, the relevant SPI signals using your DAD. So can you show us, Wes, your setup with the DAD?
Yep. Let's see.
So in the waveforms, the software, they're under the logic feature or the LSA, there's going to be a specific type of mode called SPI. Can you show them that again? Click the, no, cancel, and then click the plus again. The green plus is going to, you can specify then SPI. We talked about this a little bit in lab document. SPI is going to basically allow us to use DIO signals in a special way, these DAD signals, and it's going to infer the SPI protocol from the data on those signals. So basically, Wes can show again just show them the add menu one more time, and then we won't talk about it. Just you're going to have to set up the DIO signals and the relevant activation level, sample, polarity phase, et cetera, and you'll probably want to, we don't specify this in the lab document, but you're going to want to choose probably the format to be hexadecimal, just to see it easier. So we already set all this up the relevant way, and we have two things that we set up because unfortunately, actually, can you go one more time back to the add menu, Wes? Unfortunately, each SPI protocol only allows you to use one data line. So remember, we have two data lines. In our case, we have a MISO and MOSI. So what we care about for checking read, we want to check MISO. We want to check whether or not the master input from the slave is getting to be hex 69. So, but we can only use one SPI protocol for that. So we actually have two SPI protocols set up, which you're not going to have to do for the lab. You're only going to do this for the transmit or the MOSI signal, but we're going to show both cases here. So we're going to have a MOSI signal to show us we're actually writing the relevant data to the slave. And then we're going to show the MISO signal with the SPI protocol and show us that we're actually receiving the relevant data. And then you want to talk about the trigger and stuff, Wes?
Yeah. So if we set trigger to normal, we can specify whether we want a simple trigger, which is like a falling or a rising edge, or we can choose a protocol trigger. In our case, the protocol is SPI. So if we choose one of our SPI buses here, we can make it trigger on a certain value. So if the data is, say, hex 69, then we can trigger there, or we can trigger on a start condition, which is, in this case, the chip select going low. Same thing for a stop condition, chip select going high. And so because we want to see the whole like timing diagram, we can trigger on a start condition.
And in general, you probably want to do that because if you want to figure out if your SPI protocols and your interface is not working, you want to see all the data that you're getting. Yeah. And that's the appropriate trigger to use.
Yeah. And we've already tested this. So we've already selected a valid position and time base, but this can be done by trial and error. Let's see, we're running it and it's not triggering because, the program's at a breakpoint, it's not running. So if we reprogram this,
it should have triggered already.
Yeah, I didn't want to have to explain that. So, here we go. So we've got a timing diagram that looks similar to what we showed in the PDFs here. We go back to SPI. If I can get both of these on here, that'd be good.
So the note is the first three signals are associated just with MOSI, and then the fourth guy, which we're going to expand in a second, is going to show us the MISO line. So we're only seeing the top three in the given protocol within the datasheet right now. And Wes, you can go ahead. Sorry.
Yeah. So you can see the chip select's the same. We have it load during the whole period. We have two bytes being transmitted, so we have 16 clock pulses. You can see there's a gap here between the clock pulses. That's okay in SPI. It just has to do with how our code's set up, and any minute delays that are between transmissions are going to show up here.
Like function calls, et cetera, in our C code. That's why there's that delay.
Yeah. And then, like you said, we're only seeing the LSM serial data in pin, which is the MOSI pin, master out, slave in. And as you can see, like Chris said earlier, we have the 8F because the 8 is the read write bit being set, indicating a read from the device. And then the address is 0F in the other 7 bits. And then the next byte that gets transferred is garbage data going out of the X mega because we have to initiate a transfer so we could write any data. In this case, it just happens to be FF because that's what we chose in the code.
And that doesn't actually get written until the second set of clock pulses.
Yeah. And then at the same time, the second byte is being transferred. The data from the slave, which is the data we're reading from the Who Am I register, is being transferred back. So as you can see down here, we have this MISO bus, and the clock and select are the same signals. But you can see, let me shift this back. As you can see, we have the hex 69 here. Let's see, easier to look at this way. So that represents the data out byte.
So remember, reiterate one more time because I'm sure some people are confused still. Every clock, can you highlight the second set of clocks? Every clock on that second guy, we're going to shift out some garbage data, and every single clock is going to shift out one bit of that garbage data, and then also the master is going to receive one bit from the relevant register, which is the Who Am I register in our case, which again was specified by the F in the first byte.
So this data from the slave gets stored into the receive data register of SPI. So when you read the data register, that data gets put into the, in this case, the test variable.
And we want to wait until that whole set of clocks is set, or the whole set of clocks happens, or the whole transfer. And you're going to use that with a flag, the interrupt flag that Wes talked about in his video. We also discussed that in the lab document a little bit. But in this case, we want to actually read the data from that register after all that data has been written, that garbage data. And we can see, can you expand again the MISO line?
Yeah.
Again, the whole SPI protocol thing in the LSA, in this logic feature, basically is what creates this nice little interface that tells us what the data should be interpreted as. And that's why it's telling us, hey, we got hex 69 or hex FF that we transferred. And you could see that from the data line. If you scrolled in and looked at the clock signals, that would transfer to 1 0 bit, 2 1 bits, 1 0 bit, and then the 9, 1 0 0 1. So this is a nice, again, this is what you do in general when you set up microcontrollers. When you set up some SPI system or some communication protocol using a internal peripheral system like the SPI system of our microcontroller, you want to make sure communication's actually working. So to read from the device, we are actually just reading from some predefined register like the device ID to just make sure, hey, if we actually get that value, we should be very confident our read functionality works. And on top of that, it's important to note maybe too, or notable, that if we read from the device, we're actually also writing to the device, right? We wrote garbage data, we wrote the address, so we actually had to do write functionality as well. So when you test read functionality, you're actually verifying both write and read functionality of the SPI system. But we're gonna have you use the DAD to test write functionality separately so that you're doing it more incrementally. And then we're gonna have you do in the lab just reading from the whoami register, just like we did here, using just a variable or just some watch window within Atmos Studio. And you're not going to have you do the DAD for the receive functionality. But this is how you could do it both at the same time with MOSI and MISO. You would do 2 separate SPI protocols. So you would add the drop down again, the plus sign, and do SPI. So this is really at the high level what we really just wanted to show today, and just get across the idea of accessing the slave, talking to the slave, and the protocol that slave expects. Remember, if you use a different slave, you'd have to look at that relevant data sheet to see, hey, what is this slave expecting in terms of communication? Can it use SPI? If it uses SPI, what is the protocol that it expects for SPI? Does it use only I2C or some other system? That's why you have to know these kinds of protocols. And that's why we're teaching you SPI and mentioning I2C, because it's also familiar, but we're not going to do that in this class. But does anybody have any questions? This is a lot of information again, but hopefully it starts you for the lab. David raised his hand. Go ahead, David.
Yeah, in that image you were showing before.
I'll share again.
Okay. Yeah, I understand that the 69 is the data that came out from the slave, but is that FF? What is that?
The front FF or the back, that's top FF?
That one, yeah, the second one.
This
The
one?
bottom one.
The bottom.
Question.
Okay.
Yeah.
So just like when we want to read from the device, we have to write garbage data. When we write to the device, remember with SPI, a transfer always happens. Okay. So in this case, we're writing 8F, and that's valid data that we care about. But the slave, it has to shift out something, right? And whatever it shifts out in this case just happened to be FF. It could have been anything. It could have been what was previously in its shift register, or maybe it has like a default value of FF. But the key thing to know is the fact that it just doesn't matter what we received back, because we didn't handle it on our side.
Right. So when we, on our end, like the function we make, we have to make sure that we're actually reading the second value and not whatever the first garbage value was.
Yeah. So basically you're going to create, well, yes, but in the context of what we're doing, you're going to create basically a function called LSM6DS3 read, for instance, for reading. And that read function is going to do this first byte of data, and then it's going to transmit some garbage data. And then you're basically, that garbage data that you transmit, after you transmit that garbage data, you're going to know that whatever's in the data register after that point should be the relevant data that you were intending to read.
Yeah.
Got it. So just,
there'll always be data coming back into the data register after a transmission. It's just your job to know if you care about it at that point in time.
okay, yeah, makes sense.
Yeah,
Thank
every
you.
single clock, for everybody else, every single clock both transmits from the master and receives from the slave in our context.
As long as MOSI and MISO are physically connected.
So in the first case, we don't care what data is received because we're just writing to the device. But in the second byte of data that we're writing, we care what comes out of the slave. That was a good question, important question. Any other questions, concerns, or
Can you explain again the reason for the gap and then what's happening with the second set of clock cycles?
Yeah. So remember that in general, if hopefully you've written a couple assembly programs where there's a lot going on in one routine, and recognize, say you're polling for some flag and you do some operation, but then you do some other operations and then jump back up there. The gap between you actually doing the top thing again takes some time. So like if you execute something and then execute other things and do that in a loop, it's going to take some time before you get back to doing the other thing again. So basically here, the gap represents your processor doing other things besides transmitting SPI stuff.
Like, maybe you're saving the next byte into a variable, or you're, preparing a write function call or something. But note
LDS,
that
RCall,
this looks like a lot of time with respect to the clocks here, but look at the time base. We're in like 10 microseconds per division here, which is very fast. So
yeah, but that's actually just representing other assembly instructions or other machine code that's executing that doesn't have to do with SPI. So again, that in general, that would be like, let's say, returning from a subroutine, jumping to or calling the subroutine, pushing the status register, loading a variable from memory, storing a variable in memory, et cetera, et cetera. Does that make sense, Justin?
Yes.
Okay. Good question, though. Any other big picture questions? We have about 9 more minutes. Anything else that we want to talk about? Or, are there any questions at all about C or this? I would get started on this lab as soon as possible because of the C idea of learning C more, as well as there's a good amount of sections in this lab that it's hard. We understand if it's hard to wrap your head around the idea of communicating with some slave device using this peripheral protocol. It is a little hard to get your head wrapped around at first, but it's a very important concept that will come up again and again if you use any form of microcontrollers in your future. And
a lot of this lab is us telling you to read the data sheet for that device. So you have to be able to interpret what it's telling you to do as far as configuring the XMega. And you have to know which registers to read the data from, because you get accelerometer data and it can be in different formats, and you have to know like how fast you want it to update its registers and stuff like that. So you have to read the register descriptions and the valid sections that tell you how the device will be configured.
So an overview again, the incremental steps that you should try to think about. What we're doing first, we're going to write some functions that configure the SPI system of the XMega to be able to eventually communicate with the LSM. So we're going to configure the SPI in a manner that the LSM can appropriately handle. And then we're going to write other functions that use those SPI functions to actually write the relevant data, such as read bit, write bit, address, et cetera, to actually then write to or read from the LSM device. So we're going to try to incrementally kind of create this abstract set of application code that allows us to, at the end of the day, when we write an application, just use these high-level functions, these abstract functions that abstract away all of these low-level details of the protocol and how we communicate with the device. And then our application code is going to look really nice and clean. And there's a couple other things of abstraction we add in the lab that we want you to use and we explain in the lab. But that's the general idea that we're going to try to show when using C2, that we want to write application code in a nice readable manner. And usually we have the application code in separate, or the device level or peripheral level stuff within separate files from our application code. And you'll see that in the lab document. But one question I want to ask, I guess, before we end, if nobody else has other questions after this, does anybody feel like the manner in which we're having the lectures, posting the lectures, like watching them before, do you all, or some people, feel like you do better understand or can follow along somewhat with what we're covering in lecture, like the SPI stuff? And somebody said yes, but tell us if you don't think so either. We're trying to make the lecture stuff pretty condensed, pretty concise, what you need to know. And we want you to be able to follow along. And the idea, again, is we think that this class, we think that this class is, more about the application practical content. So we want to condense the theory and then apply it more in class. So it seems like a lot of people are saying yes. Nobody's maybe saying no if they're afraid to, but offline, if you want to tell us too, please do, because we want to figure out for the future, we're going to keep experimenting in the future semesters, and maybe eventually we'll fully flip the class in this format. Yeah. So somebody said the length makes it worth it. I think shorter videos, you're saying. So yeah, that's our goal too. We don't want to make you spend too much time. And there is no honor lock for the attendance quiz. Maybe you mean the lecture quiz, but we're going to keep doing honor lock right now. Again, I think that most people just probably weren't prepared for doing honor lock.
It seemed to go pretty well today. So
yeah, I think people just, once you guys prepare a little bit more and get used to it, it's not a big deal.
And your desk stays cleaner, right? So it's a plus.
Yeah, we always want to make references to manuals. Just recognize in the past, Dr. Schwartz just hasn't had the time to cover all this stuff in class. So that's been an unfortunate reality for any lecturer that's responsible for covering the theory and anything else in class. So it takes a huge effort to do so. Somebody said lecture quizzes being worth a whole homework doesn't seem to match up with how much work is put into homework versus quizzes. So yes and no, but recognize, so that might change in future semesters. We're just experimenting right now, but the main idea of the lectures is we want some incentive for you watching and studying the stuff before you come to class so that mainly you can follow along in class. That's the main idea of the lecture quizzes. So we don't want to make them worth too much because you haven't actually gotten exposed to the material yet to really, when you actually do the content, that's when you really start to understand the content normally, use it. So
yeah, and we think that watching these videos is just as important as doing a homework. Like because if you don't watch the video before the Thursday lecture, then you really miss out on actually understanding as much of the material as possible. And that's just as much of a detriment as like not doing a homework, for example. So
but I think they were also saying that maybe it should be worth more. Is that what you're saying?
I thought they were saying the homework should be more. But maybe I just misinterpreted.
I could have easily misinterpreted too. Maybe they'll respond and say. I'm looking at their chats too. So the Thursday lectures at the actual help session portion, we do expect to post, I believe still. That's the idea, because we want to have, ideally we'll see some set that you can review to and for your labs and stuff, and try to keep it help oriented.
And we also, part of it was we didn't want to completely restructure the grading rubric, because the first half of the class still had to be, the same as far as point values. So future semesters, it could be reevaluated, but.
We'll recognize too, the homework, when it's split up amongst all the homeworks, all these lecture quizzes, it's not worth too much of your grade ultimately. Again, it is about 0.5% of your grade probably overall, but I think that's maybe a little bit less if anything, but that's a decent amount, we think, for making sure that you have some incentive to actually do watch the content before we come to class. Because if you guys don't, then there's a lot of people that are just sitting idly by, which could be the case right now. That's what I wanted to hear, that don't really feel like they're following along still, but we're trying to minimize that.
When the semester's over, what we're going to do is look at a correlation for the lecture quizzes and how people do. And if we see people do poorly on lecture quiz, then we know they probably didn't watch the videos or watched them in fast motion or watched pieces of them. And that'll give us a lot of information. But there are very few homeworks. What do we have? 3 homeworks, though.
Yeah. And the homeworks are Zen graded, right? So.
And homeworks are, mostly.
Thanks for the feedback, though.
Yeah, and again, we're trying to help you guys as much as possible, but we do want to, again, make a conducive environment to you actually learning and actually forcing yourself to learn. So that's why we have the big lab quizzes and stuff like that. We want to actually make sure you yourself understand how to apply the content, not that you just worked too much with friends and you, again, reason we're not doing a note card too probably is if you just, for one lab, if you write so much stuff, little tiny font of all this code, that doesn't prove that you actually know how to apply it. And so most of the time, we're probably not going to have a note card, but on the exam, we will. I understand that could be frustrating to some people, but it is about learning the content and learning how to apply it. So please understand that. Any other last minute questions or concerns?
I got one. It's not really related to like the class structure stuff, but this LSM chip, it says it's an inertial measurement unit. Mm-hmm. So is it meant to communicate with stuff that can pick up on like those types of measurements, or is it like if I move? Oh, so if like I move my my memory baseboard. I mean, not the
Micropad.
the whole micropad.
Yeah, yeah.
Then it should pick it up.
Yeah.
Yeah, you can use this as an accelerometer,
That's what we're
or
gonna do for
actually
the
you can
lab.
rotate
Yeah.
it. That's what you're doing.
So basically,
And,
like acceleration, this accelerometer is going to pick up the acceleration forces. So if you have the backpack flat, the IMU, if you figure out how it's positioned on the micropad and the robotics backpack, you actually see it should be the Z-axis. There's going to be X, Y, and Z for accelerometer data, coordinate axes, and acceleration force of gravity is always going to be acting on the accelerometer. So you're actually going to see that in the lab. If you rested your micropad in one direction on your desk, you'll actually see acceleration forces regarding gravity always getting acted on the IMU. But if you were to move your device around too, you'd see all different forms of acceleration forces being picked up by the IMU. And then the microcontroller is actually reading from the IMU using SPI to grab that data that the IMU converted from the measurements into actual digital data. And then the microcontroller interprets that digital data, reads from it, and then your application handles that data.
And in the lab, you're going to actually plot the data. So if you wave your micropad back and forth, you'll see the actual signal that represents the acceleration forces. And like if you rotate it, you'll see like the position or which axis has more or a higher force value associated
with gravity and stuff like that. Yeah. And we're going to plot the X, Y, and Z data, just like Wes said, and we're going to use actually another program on your computer called Serial Plot. There's various out there, but Serial Plot's pretty nice. And what we're going to ultimately do, so it's you can hopefully see after the fact, it's going to be a nice big complete application. We're going to use SPI to configure the IMU to have the accelerometer enabled. The IMU is going to have data. And then whenever the accelerometer has new data for us to read, we're going to have an IO port interrupt, tell the microcontroller, hey, you have data to read. It's going to use SPI to read that data. And then it's going to take that data and it's going to transmit it using USART to your computer, where your computer using serial plot then is going to interpret that serial data and then actually plot it using an appropriate format that you transmit. And then you're actually going to see all that happen in real time. Your accelerometer data get plotted real time on your computer. So you can start to see how all this is coming together. And it's really cool stuff. And there's so many more applications out there, but this is one applying SPI using your IMU that expects SPI.
Yeah, that's pretty cool.
Yeah. Any other questions? We're going to go ahead and wrap up here. You guys can go ahead and leave. If anybody has questions, there's at least one person that had a question after the fact, you can ask. But I'll go ahead and stop the recording. You all can leave. See you next week and prepare for USART quiz next Tuesday.